This morning you heard a lot about the history and the philosophy behind the AMP Lab. You heard a bunch of perspectives from other outside voices about AMP Lab and big data, and you heard the word SPARC mentioned a bunch of times. You heard the word, the name Matei mentioned almost as many times, and we now have a talk that combines both of those words. I have with me here Professor Matei Zaharia from Stanford, and he's gonna give us his retrospective on SPARC. So thanks, Matei.
All right. Okay, thanks, Mike. Thanks, everyone, for stepping back in from the really nice day outside to listen to this. So this is a talk I created actually a few years ago. I gave it at one of the AMP Lab retreats too, but now it's updated with new ideas, which was kind of a fun talk on 3 ways that SPARC went against conventional wisdom. So basically, like, I mean, the high level bit is like, you know, we had a pretty small team at the AMP Lab, regardless of like, you know, how you know, like basically how many great students and faculty and stuff there are. And nonetheless, like through this project, we were able to build something that was useful in both industry and led to interesting research. So how can you do that with a small team? And I think a bunch of that came out of these 3 kind of unconventional things we did. These are things that we were in some ways forced to do because of the limited resources, but they were interesting things that then led to a bunch of new ideas. So I'm going to talk about the 3 kind of unconventional things we did in the project, and then I'll talk, finally, I got permission to add in like a tiny bit of stuff that's going on at Stanford about one research thing that is trying to take them further. All right, so without further ado, let's look at the conventional wisdom and at thing number 1. So thing number 1 was building a query engine, like a SQL query engine, on top of MapReduce. So back when we were starting the project, there was this whole, you know, MapReduce had just kind of come out and gained prominence in some workloads, but they were mostly these sort of ETL and batch processing type of workloads. And there was also a lot of kind of backlash against it because it did away with many of the things that were done in parallel database engines, which had existed for a while. And in particular, there was this paper, for example, that tried to evaluate them and tested some workloads on MapReduce versus on an anonymous sort of parallel database, and found that basically for SQL query workloads, these MPP databases were 10 to 100 times faster than MapReduce. So that was kind of the thing. So how come we at the AMP Lab decided to actually build our SQL stuff on top of SPARC? So first, let's dig into why these databases were faster. So basically, there were 3 different things that this work found. First of all was data representation. So databases were schema-aware, column-oriented, and so on. MapReduce was all about these records of unstructured data, and you know, they didn't know anything about what's inside them. The second thing they found was indexing, definitely helps. And the last thing was the lack of mid-query fault tolerance. So they said, oh, MapReduce jumps through all these hoops to make it be able to recover in the middle of a job, and that adds overhead compared to just pushing data between a bunch of operators in these databases. So that was kind of the background and why people thought this architecture wouldn't really work for low latency query processing. So what did we do about it? So we published a bunch of things doing SQL on SPARC, essentially. The first of them was Shark back in like 2012. And then SPARC SQL is kind of a descendant of this that's being developed today. And basically what we found is, you know, by building basically a SQL engine on top of SPARC instead of MapReduce, just plain MapReduce, we were able to get that 10 to 100x speed up, and basically we were able to get something competitive with these MPP engines. So what was different between SPARC and MapReduce? Actually, there's not much that's that different. You know, like people maybe talk about, oh, it's super different all the time, but there's not that much that's different. So SPARC basically lets you do general graphs of MapReduce operations. And it also adds this ability for in-memory data sharing between the operators. But the operators themselves are still essentially map and reduce. They're not particularly different. And then the final thing that Spark did that you didn't have in the existing MapReduce implementations is we designed it for much lower latency. We designed it so you can do a whole MapReduce job in 100 milliseconds instead of, say, a couple of minutes, which is kind of the minimum timescale you got with stuff like Hadoop, because that was designed for workloads that take many hours. They didn't really care about latency. So this is really all that was different in it. And with these kind of small changes, which just added basically more complicated graphs of operations and data sharing, we were able to do pretty well. So what about the things I brought up earlier in that database paper on the two systems? Well, data representation is definitely important, having column-oriented and schema-aware stuff. And what we did in Shark is that we just took the same representation your database would use, and we put it inside MapReduce records. So in Shark, one record from Spark's point of view was actually a bunch of columns for a little batch of data. And that's really cool because you get all the benefits of the distributed engine, which knows how to deal with a bunch of records and does fault tolerance and all that, and you get the benefits of the schema format. And this is something now that's being used in all the other libraries on Spark, is specialized format on little batches of data. Indexing is still possible to do in MapReduce. You can read an index, and file formats like Parquet in the open source world have an index built in. And finally, mid-query fault tolerance, we have it in Spark. It's on by default. You can't actually disable it. And we found that the system still performs OK. So it's actually not as big of an overhead as people thought. And the other cool thing about fault tolerance is it also enables you to do stuff like scale the job up and down if you want to add more machines in the middle, or if you want to remove half the machines, the engine supports that, and mitigate slow nodes or stragglers. So that was kind of the conclusion from here, is you can take a lot of the tricks in these database engines and do them in a MapReduce-like system and get sort of the best of both worlds. So that's the first thing I wanted to highlight that was unconventional. So the second thing we did that was unconventional and that kind of came to define the project later on was one-size-fits-all design. So this is, again, looking at database papers, because that's a field where people have strong opinions, so like it's easy to to point to an opinion. So basically, the opinion was one size fits all is an idea whose time has come and gone. Databases at the beginning were supposed to be this kind of magical piece of software that does anything your application might do involving data, whether it's analytic, batch stuff, whether it's point updates, all this stuff is handled by the engine. And then people decided, well, with the growing sort of trade-offs in how you store data and how you use hardware, it's really hard to make one-size-fits-all systems. So we should move instead to specialized systems for each design. Even for, like, if you have scientific data versus just tables, that should be a separate system. And it does make sense at a high level that if you have these specialized systems, they'll be able to do better at each task. So that's kind of the conventional wisdom there. In fact, even in the AMP lab, or maybe I guess this is in the RAD lab technically, we also had this idea that, there won't be a single programming model for the data center or that will cover everything. And actually the whole Mesos project, or this is the earliest thing on it, which was when it was called Nexus, said that there'll be lots of these programming models and we need a way to just have them coexist. So basically, we went from this kind of one-size-fits-all database system to many separate ones for each task. And basically, the question was, are we ever going to come back to a single one, and would it make sense? Are there any benefits to that? So as people started adopting these things, clearly the specialized systems could do a bunch of stuff. But there were also some problems with them. And basically, we worked with early users of these, and we found a bunch of problems. one of the problems was management. It's all the joy of installing and administering Hadoop. Now you have to do it for 3 or 4 different systems. It's not that great. It's a lot of overhead, and it's a lot of pain to do something like that. So that's one problem with separate systems. Second problem was resource sharing. When you have a big cluster of machines, how do you actually dynamically share them between these systems? And it's especially hard for big data because data, you don't want to move the data over the network to each system. You'd like to keep it in place and move the computation to it. So that's what the Mesos project really tried to address. And then the final thing that was kind of a nail in the coffin of this was performance. So real workloads, both back then and today, real data science workloads and applications combine many different processing types. And in this world of specialized systems, they had to combine many different systems. And then you can't really optimize or share data efficiently across them. So with all the systems built on the Hadoop stack, for example, you had to basically write stuff to a file whenever you want to push it into the next system. And that could be way slower than like the computation you're trying to do. So these were the problems with specialized systems. So what did we do in Spark? What was our approach? Basically, we said MapReduce turned out to be pretty good for SQL queries. So let's just try to use that for everything else too. Let's kind of push the limits of what we can do with it and see how many of these workloads from the specialized systems we can actually do using MapReduce. So when you wanted to do graph processing, instead of building a new engine for graphs, we just tried doing iterative MapReduce. When you wanted to do streaming, instead of creating a new engine for streaming, in Spark Streaming, we just ran many small MapReduce jobs and used them to update some state and compute some stuff in parallel, and so on. Machine learning, time series, all these kind of workloads, we just tried to do them with MapReduce. And we found that actually once you spent a bit of time doing this, you could do most of them pretty well. And then you got these really cool benefits because they're all on the same engine. They're very efficient to combine. You have to do a lot less work to build each one. You reuse the stuff you wrote before and so on. So that kind of let us, we quickly shifted our approach to, to just doing lots of stuff this way on top of Spark. So that kind of led us to ask, like, okay, why was MapReduce so general? And the interesting thing here is actually, if you look at it, you should expect the model to be pretty general. So if you ask, like especially back, back a few years ago, people were asking, okay, what distributed computations can MapReduce capture? What are its limitations? Which ones can it do efficiently? The answer, if you actually look at it a little bit, is it can actually capture any distributed computation, and in many cases, it does pretty well. And I'll explain exactly what I mean by that later. So if we look at MapReduce, this is one MapReduce step. Basically, you have 2 pieces. You have the map and the reduce. In the map, you're doing local computation on the data that's on each node. And in the reduce, it lets you send messages from any node to any other node. So it's like this all-to-all, potentially, communication pattern. And that's what it is. And now if you use this primitive multiple times and do more MapReduces, basically you've got a system where you can do some local computation on each node, and then you can exchange messages, and you can keep alternating between these 2 things. So if you think about that, any other distributed system you might write could be emulated by this type of system. Like any distributed system you have is going to have some code running on each machine and then some messages being sent across the network. And sure, here we're making them be synchronized somehow, but basically, we can kind of emulate whatever distributed algorithm you had in your own system using this thing. And in fact, this kind of simplification of distributed computing with these separate communication steps is called the bulk synchronous parallel, or BSP model. So it's actually a model that's used to analyze and develop parallel algorithms. So that's why any computation can kind of be emulated using MapReduce. And the final thing we asked about this is, okay, what makes this emulation efficient? Like, when will it be fast and when will it be slow? And basically, there are 2 things that can that affect its efficiency. One of them is we're going to need multiple steps So how quickly do we share data between these steps? And that's an important thing. In something like Hadoop, there was no notion of a multi-step MapReduce job and of sharing data between them, but that's an important thing. And the second thing is, how high is this communication latency? If this is super high, then we'll be emulating a system that's running on some kind of very high latency network, and maybe not all algorithms will do well. But on the other hand, if we can make this pretty low, it doesn't add that much overhead that we're waiting and synchronizing. So in Spark, we actually tackle both of these things through the stuff that we happen to do in the engine. For the first step of sharing data quickly, we had this concept of RDDs, where the whole point was you can keep data sets around in memory or on disk and share them efficiently across many MapReduce steps without writing them to a file system. So we sort of solved that first problem. And for the second step, we spent a bunch of time optimizing this. It's still not perfect, but we were able to get reasonable MapReduce jobs happening in 100 milliseconds. So if you've got an algorithm that would be OK with 100 millisecond latency, then it can do OK on this type of system. And it turns out many distributed algorithms were just fine in this space, and so they did OK. So that's why basically MapReduce plus the small additions that Spark added in terms of data sharing was actually able to do pretty well in these things. So that's kind of, that's why it worked. Now, what were the benefits of this? So there were a couple of really cool benefits from having this one-size-fits-all engine. The first thing is that any improvements we make to the engine help all the applications on top of it. And remember, again, we were a small, kind of tiny research group trying to do stuff, so it really helps to have that multiplication of sort of benefits when you do some effort. So, for example, when we built Spark Streaming, we spent a bunch of time really minimizing Spark's latency. Just after we added that code and we started running our experiments for Shark again, which was the SQL engine, we found a lot of those were running 2 times faster. So that's pretty cool. Some students worked on Spark Streaming and someone else's project became 2 times faster. That's definitely nice. And then the second thing it let us do, which users take full advantage of today, is it lets applications mix these different processing models efficiently. And you get some really cool new applications that you couldn't do before with the separate systems. Like if you've got streams, but you want to do ad hoc SQL queries on them, or if you want to join your stream with offline data or stuff like that. So these were the things we got. So to show you kind of how much impact this has, I also wanted to show one picture of kind of what these systems look like at the end of the, basically when I left AmpLab and went to work on this stuff commercially back in 2013. So back then, we had built all these things on top of Spark, and we wanted to compare the code size and also the performance with the different engines that existed on Hadoop. And back then, the Spark system was only about 25,000 lines of code. Even now, the core engine part of it, I think, is about 50 or 60,000, so it's not like enormous. And we look at, okay, so as an engine, it's small. This is written in Scala and stuff, so it's a bit unfair in some way because it's a different programming language. But the other cool thing is if you look at the different functions on top. So for example, for SQL, the Hadoop community went out and built like these separate SQL engines such as Impala. And we just built this layer, Shark, which was much smaller than a full engine, could just use the existing Spark engine, and could still do competitively on SQL. For streaming, people build systems such as Storm. We built a little library, less than 10,000 lines of code on top of Spark to do streaming. And for graphs, the same thing. Instead of a separate graph system, we had this small thing here. So we ended up with spending a lot less work and reusing the work that's in the common engine and being able to do all these workloads in this one stack. That's really like kind of what was needed for a small group like ours to do it. And then when you look at performance on all of these different workloads, the systems were basically competitive with what was out there. They weren't always the very fastest, but you could put in the optimizations that everyone did in terms of data layout, computation, and so on, and you can get pretty close. So that was kind of a cool thing, and one of the most maybe unconventional but interesting things that came out of the project. Cool. Okay. And then the final thing I'll talk about, just kind of for fun, is another unconventional choice we did, especially at the time, which was to use this high-level implementation language. So, if you're looking to write a high-performance data processing system, you have a few choices in terms of programming languages. So you might choose something like C. This is probably the choice if you're a commercial systems developer working at Oracle or something like that. If you're really sort of like, living on the edge, working at one of these trendy web companies, you might go with Java or Go today. That's like, okay, it's a bit more managed. It'll let you get the job done faster, and you can still build these kind of systems. But we decided to go with Scala, and especially back then, this was a pretty academic choice. Actually, today, more people are doing this stuff, but certainly back then, that was the thing. So that's what we did. So why did Scala work? Definitely this happened to be aligned with like the trends that happened in programming languages. But there were also a few reasons why it ended up working really well for Spark regardless of that, not just in terms of like people using it. So the first reason was to do with performance. In a lot of these systems, especially back in 2010 when we were working on this stuff, the bottleneck was really network and disk I/O, not CPU. So it didn't matter that you had a bit of overhead from Scala in all the stuff you're doing on the CPU. You just had to not send lots of stuff over the network and try not to read it from disk too many times, and you were in good shape. And then the second thing is having this high-level API, like this functional programming API, or later we moved to stuff like data frames, which is more of a DSL, let us do more optimizations under the hood. And doing these automatically for the user had a lot more impact than telling them to write their functions in C. So that also helped. The second reason was ease of development. Again, we were a small group. We wanted to build these systems that are like fairly reliable and have a bunch of optimizations and stuff really quickly. And we really took advantage of the things you could do in Scala, functional programming, actors, stuff like that, to build these systems really fast. And one cool thing is most of the group that worked on Spark, including myself, had not used Scala before starting this project. So we were able to still pick it up and use it in a meaningful way to do some cool stuff with it. And then the final thing where I think it helped was community. The first users who used Spark, who just like downloaded off a web page from Berkeley, were actually really advanced. They were excited to actually try something written in Scala for big data processing. There wasn't that many people at the time. And these users, in turn, built some really cool applications. They contributed great patches back and stuff. And that attracted new users because people saw, OK, you can do really exciting things with this. So that also helped kind of create interest in the project and create a really strong community around it. So final thing I'll put on this is just a note of, OK, if you're trying to do research, as an academic, you're really trying to just prove or disprove various ideas very quickly. And basically, if that's actually your goal in life, you should be trying to use the most productive tools possible. You shouldn't be spending all your time writing like a zillion interfaces in Java if you're just trying to make an argument about programming model or something. So I think even from that point of view, it made sense that we use this kind of language to build this project just so we can get those research results faster. Cool. So that's kind of the three things I wanted to bring up. And clearly, this thing also was aligned with how more and more of the industry moved towards Scala. So in the final little bit of the talk, I'm going to put in a tiny bit on stuff that I'm working on next related to these ideas, which is this project called Weld that we started at Stanford. And this is really taking these ideas of a unified engine and optimizing across the layers to sort of a next step. So basically, one interesting thing that's happened since Spark came out is that the bottleneck in big data has really shifted. Back then, as I said, network and disk I/O were really the main thing slowing you down. But if you look from 2010 till now, the commodity versions of those have gotten about a factor of 10 faster. So you have 10 gigabit Ethernet instead of 1. You have SSDs instead of hard disks, and so on. So actually, when you measure these applications today, and other groups in the AMP lab are doing that too, the bottleneck is often use of CPU and DRAM as memory bandwidth. How do you use those? And that's pretty different from what existed before. And that's likely to continue as well because the gap between these things is growing. So one interesting consequence of this is that the way that we build applications today, even on a single machine, the way we hook together data-intensive applications is not going to work in the future. So today, when you're a programmer, you're trying to build some kind of application, you bring in a bunch of libraries. And the whole idea of libraries is like experts will sit down and write various functions that are optimized, such as the BLAS functions for linear algebra. And you're just going to call them, and you pass each function a pointer to some data in memory, and then it goes ahead and computes on it. But as I said now, so now the bottleneck is really talking to memory, accessing DRAM. So this method of calling these separately optimized functions is inefficient. You spend actually most of your time just moving data between the different functions. And it's very similar to the specialized frameworks I talked about on clusters that were sharing data through the file system. Now they're sharing it through DRAM. It's of course faster, but it's still nowhere near as fast as the number of cycles per second you could use to compute stuff. So it's kind of an interesting shift that happens because of basically the growing gap between DRAM and CPU. So that's kind of the change that's happening. So how do we address this change? Basically, in this Weld project, we're trying to change the interface between libraries in order to allow more powerful cross-library optimization, so not to have to materialize data after each one. And basically what we're doing is we're taking these diverse analytics libraries and mapping them to this very simple common intermediate language. It looks a little bit like the functional operators in SPARC, but it's actually meant to be a generalization of SPARC. It also supports things that you can't do in SPARC, such as nested parallelism. And then once we have them all in there, we can optimize across them the same way that SPARC does between its high-level APIs and map them to different types of hardware. Instead of having to save data kind of naively between them, you can get much faster code for the specific set of operators you combine. So how much of an impact does it make? Does it actually matter? It turns out that it does. Even if you take these in-memory systems today that people have spent time optimizing, if you use Weld to actually optimize across the different operators in them, you can get around an order of magnitude speed up. So we ported Spark, SQL, Pandas, and TensorFlow to run on top of it, and depending on the workload, you can see these speed ups. And these are systems that have spent a bunch of time trying to make it fast, but it still makes a difference. And the other cool thing you get is, much like in SPARC, you get optimization across different workflows. So if you have a workflow that combines, for example, SPARC and NumPy, you get these really big speedups by optimizing across the two, which is something that the current engines don't understand. So this is really taking these same ideas of unified engine and data movement optimization and applying it at a much smaller scale within a machine. And it makes a significant difference. Cool. So just to conclude, SPARC got really far by just taking a super simple model to an extreme. We just took MapReduce, we added data sharing, and we just said, what else can we do with it? And we found out that we could do a whole bunch of stuff. And that's a great way to get a powerful kind of unified engine. It really highlighted the importance of this unified runtime for both usability and efficiency. And I think the same ideas can go further, and they will have to go further, actually, if we want to efficiently use the hardware of the future to sort of build applications. So thanks, and stay tuned for more stuff.